In this video, we're going to pick up where we left off last time and do one or two examples where we're going to verify that a whole family of solutions works for a given differential equation, and that family of solutions is going to contain one or more generic constants. So let's look at 21 as an example of this. The differential equation is dp dt is equal to p times 1 minus p, and our given family of solutions is p is equal to c1 e to the t divided by 1 plus c1 e to the t. So we can go ahead and differentiate both sides with respect to t right away here. Dp dt for our left-hand side here is going to be equal to, and then derivative at the top is going to be c1 e to the t times, let me just give myself some space here, left-hand side, dp dt is equal to c1 e to the t times the bottom minus derivative of the bottom is going to be c1 e to the t times the top all over the bottom squared. So left-hand side here, dp dt is going to be equal to c1 e to the t plus c1 squared e to the 2t minus c1 squared e to the 2t over 1 plus c1 e to the t squared. These will cancel. My left-hand side will be dp dt is equal to c1 e to the t over 1 plus c1 e to the t quantity squared. And on my right-hand side of the equation is p, which is c1 e to the t over 1 plus c1 e to the t times 1 minus c1 e to the t over 1 plus c1 e to the t. So when I make a common denominator here in the parentheses, I get 1 plus c1 e to the t minus c1 e to the t over 1 plus c1 e to the t. And these will cancel in the numerator, leaving me with c1 e to the t over 1 plus c1 e to the t times the quantity 1 over 1 plus c1 e to the t. Multiply straight across, I get c1 e to the t in the numerator and 1 plus c1 e to the t quantity squared in the denominator. That matches left-hand side and right-hand side. So that's a solution to my differential equation. Let's go ahead and look at 23 as well, which is d2y dx2 minus 4 dy dx plus 4y equals 0. And I have given to me my family of solutions y equals c1 e to the 2x plus c2 x e to the 2x. Okay, so we'll need to get to the second derivative here. So y dy dx is equal to 2c1 e to the 2x plus c2 e to the 2x plus 2c2 x e to the 2x. So I'll call that dy dx is equal to 2c1 plus c2 e to the 2x plus 2c2 x e to the 2x. And then when I take the second derivative, d2y dx2, derivative, this is going to give me 4c1 plus 2c2 e to the 2x plus 4c2 x plus 2c2 e to the 2x plus 4c2x e to the 2x. So let's go ahead and combine those. X2 is 4c1 plus 4c2 e to the 2x plus 4c2 e to the x e to the 2x. So we're going to have d2y dx2 is 4c1 plus 4c2 e to the 2x plus 4c2 x e to the 2x. Then I have minus 4 dy dx. So that's going to be minus 8c1 minus 4c2 e to the 2x, and then minus 8c2x e to the 2x, and then plus 4y. So plus 4c1 e to the 2x plus 4c2x e to the 2x. So 4 plus 4 is 8, minus 8 is 0. 4 minus 4 is 0, so I have 0. 4 plus 4 is 8, minus 8 is 0. And is that equal to 0? It most certainly is. So I have a solution to my differential equation. It does not matter what constants go there as long as they're real values right now. Those generic constants, C1, C2, can be any real numbers, including that either or both of them could be 0, and this would work. All right, more on that later as we get into general solutions and particular solutions and things like that. But just wanted to show you some examples here of some general solutions that we could verify as solutions to the differential equations that still contain these generic constants in them. That's it for this video, and we'll come back next time and start talking about something a little bit different. So that wraps up this this discussion for this section. Come back next time and talk about a different section. See you for the next video.